Okay, I think now recording is okay. It starts recording again. I'm not sure how many minutes I lost in during the. Let me check now. Okay, seems like I missed most of the recording. Seems like so stupid. Okay. Okay, so let me introduce any group 4 super 40 any group 4 super mouse. So this can be obtained by 10D n equal to 1. I think n equal to 1. So for filtering super mouse on R 1,3 times T4. So the action is given by like this way. And trace of okay, so this is the action of 10D mLs. Then, so we just decompose the follows. So the M, so M runs for M and N runs for mu. Mu, and the XI. I runs for 1 to 6. So 1 to 6 is sorry. I think this is P6. So in total 10 dimensions, 6 I runs from 1 to 6 is coming from gauge field on T direction. I call it small m, small m. Then, so then, and also, yeah. So mu runs for, of course, 0 to 3. So then, plus, so this is scalar part, and then the other part follows as the as follows. I mean, it's better to. It's a good exercise to do. So again, G mouse to lambda bar and M xm lambda. This is minus sign, and the minus G squared mouse over 4 xm xn. So as you can see, so here this covariance derivative is indeed dm can be written dm minus I n. Okay, now for if you have the if you decompose the gauge field in 1 plus 3 direction and a scalar field. So then this part is appear in here, and this computation at the square part. So this xmn really come from this 10-dimensional part of the field strength square, and also this xm lambda come from the covariant derivative part. Okay, so you can easily see that. So this is the kinetic term really come from the 10-dimensional field strength square. So this is how you obtain by dimensional reduction from 10D to 4D of the super young band. This is the action of this 4D n equal to 4 super young bands, very simple. And then so this is GMLs, and we can also add the following topological term. I theta 32 pi square trace of Poincare number and jet. So here the parameter theta is called theta angle. Eventually you can combine with the GMLs so that you can have a complex Spider Kaplan constant. So it has a very simple supersonic transformation. Delta xm is a minus e bar delta m lambda delta nu is minus e square bar gamma mu. So this is supersonic transformation. Okay, so this action is invariant under this supersonic transformation. So it's very simple. In 10 dimension, the supersonic is more simple. Sorry. So you can imagine, right? So you have a 10 dimension instead of this is supposed to be mu. Instead of mu, you have a capital M. And you just have this time. You can forget about this. It's very much more simple. And then the nice thing is the classically you can just have a dimension. So what is the dimension of GMLs? What is the dimension of GMLs in classically? Zero. How do you see that? Mass dimension is 0. How do you see that? Mm-hmm. So from this action, so the derivative has mass dimension 1. So the nu has to have the dimension 1 too. So this one has dimension 2. Okay, so therefore f mu is dimension 4. That cancels with this measure minus 4. So it should be dimension. Classically, the GMS has to be dimensionless. But in quantum mechanically, this is not the case. If you do the scaling transformation BGML, usual quantum field theory is non-zero, like QCD. QCD beta function is non-zero. But in fact, for the n equal to 4, if you compute the one-level determinant of UN, it's indeed 0, or in more generally, for the n. So therefore, this means that the for the n equal to 4, super MS is quantum mechanically conformed. Um, and in particular, so this and the supercharge has the following following symmetry that the so therefore compound symmetry, so it have SO2, 4, and there is an R symmetry SU4, R symmetry. This is exactly what I have written here. Oh my goodness. Yeah. So this is compound symmetry, and the SU4 is R symmetry, coming from supersymmetry. Okay. And then, moreover, you can just have the complex coupling constant here that receives the action of SF2Z. So this is a property of the for the negative Fourier mass. And let's move on to it is file background or near horizon of this geometry. So as I mentioned, so this the for the negative 4 is the engineer ellipse on the stack of ND3 brane on the type 2B string theory. And we just look at the near horizon geometry of this D3 brane. So to see the near horizon limit of this D3 brane, you use the supergravity theory, so that the which we did for D1 D5 system. Oh, what was a choke? So in the D3 brane, maybe it's better to write it from here. So near horizon geometry, I mean, so as I mentioned, so the D3 brane has the charge and also D brane charge and the D brane tension. So therefore it has a mass. Okay. So therefore there is a back reaction to the geometry. So that the ds curve is the metric is as follows. So it's very particular feature for where this C4 is Ramon flux. Which is the this is very universal feature of the supergravity theory around the metric and the Ramon field for around the D brane. So this H is often called harmonic function, and then H of y is taking the following form. And what R4 is the 4 pi G string number of n and alpha prime square. So this R4 is kind of radius of geometry, and which is proportional to the string coupling constant and the number of the E3 brane and alpha prime square. And if you look at the crossing, you look at this metric, it takes the following form. So y goes to very big. Of course, y is if very big, you can ignore this one. So h is indeed 1, right? Almost close to the 1, so that you have just flat metric 1. It's just 1 times the flat metric, 1 times flat metric. Okay. So therefore, space-time is very flat. The y goes to, it's the flat metric. On the other hand, if you take the different limit, so y is less than r. So then, so much less than r. So then this term becomes dominant in harmonic function. Okay, this term is dominant. And then you have to take into account this term, and if you introduce u is equal to r squared over y, and then rewrite in terms of metric u, this metric can be written as follows. Okay, so this is the becomes the metric here, and then here, if you look at this one, first part is indeed AS5. We just look at the Poincare metric. Poincare metric I have written down. Just the first part of the lecture, and this part is S5. So if you take, yeah, of course I take this is very big. If you take the r squared over y, is very, very big. Indeed, the metric look like throat. And here you have a bunch of ND3 brain cells. Okay. So metric look like this way. So where the and then if you take the following limit, y goes to 0, and alpha prime goes to 0, and u take to be r squared over y is fixed. Even though it's very large, it's fixed. Then, so this limit is called, if you take this limit, the metric like this, and this is AS5 cross S5, and since the r is also r squared AS5, and r squared S5 is alpha prime 4 pi n gs squared. So in other words, I just take the square root of this guy, and take it takes a nice limit so that the alpha prime also will go to 0, but the ratio between r squared and y is keep fixed. Okay. Keep fixed. So this is it's called double scaling limit. Y goes to 0, alpha prime goes to 0, but the ratio is keep fixed. In this case, indeed, so here near horizon, is indeed it becomes r is very small. So this is r and the radius r almost, and then so the asymptotic flat region is decoupled from the region in this road. So if you have the wave is the how to say, the y is very big, the physics at the how to say, the asymptotic flat region is decoupled from, do not talk to each other, the physics near horizon, okay, near d brane. So that's why the people call it's called decoupling limit. This called is decoupling limit. Yeah, so that here, so y is very small, y is very small, and y is very large region do not talk to each other physically. So then, once you take this decoupling limit near horizon, the metric really look at it is 5 cross S5. So now, we just see the relation between it is 5 cross S5 and then for the n equal to 4, mouse. And so this is the motivation of what the Maracina conjecture the relation between large n limit of for the n equal to 4 UN mouse, super mouse, and also gravity theory or supergravity, or more generally string theory, living on ADS5 crosses. So from here, we will a bit more precise about what's the equivalence relation between them. And in particular, it's very tempting to, indeed, I mean, this, as I mentioned, open large and limit is in the first proposed by actually in 1974. So he predicted the large and limit of Yang-Mills. It's described by actually string theory. At that time, the conjecture is too bold, and then too bold to be very concrete. But this is one of the example, and to prove the idea become concrete and able to check. And then to prove that, introduce Poincare constant. And so nowadays for the fruit coupling. And if you compare with the this one, oh my goodness, this guy, and this guy, it's very tempting to identify GS is equal to G Yang-Mills squared. If you take this one, indeed, this so when the radius of the ADS5 and S5 is very big, is indeed, so the R squared divided by alpha prime is very big, is equivalent to this foot coupling is very big. And then so what Marcel conjecture is in this region, so the 5D, type 2B supergravity action, supergravity or string theory, sorry. Yeah, so in this instance, supergravity action is very, very, since here alpha prime is also very small, so that the supergravity theory description is valid, is large n limit. Limit of 4D, n equal to 4, So this is the Yeah. And then so capital N is the indeed turns into the flux of S5 or to the field strength self field strengths in type 2B string theory can be identified. So this G5 plus is the Ramon field strength of Ramon Forfan. So you can just identify this the number of the three brane as a flux supported on this S3 S5 sorry S5. Okay. And then more generally, so you can just consider the follows. So this is the supergravity limit. Maybe you can just fix. So here lambda is very large. You can fix the lambda is fixed, but n goes to infinity. Then so this is called at Hooft limit. So this is supergravity limit. This is supergravity limit. But this is called Hooft limit. Here, so you can just compare with the so you can just consider so this G string as lambda over n. So if you fix lambda is the finite and the n is the very big, GS is very very small, so that indeed you can just consider this is the type 2B string theory where only planar diagram contributes. It becomes dominant. So in this limit, as I mentioned, so I don't draw the so for instance, planar diagram is something like this one. If you consider open string, so this is planar diagram, but not planar. It's this one. So here you can just this is not planar. No planar diagram. So which means that you can put this one into the torus, whereas you can put this one in the sphere, whereas you can put this one in you have to put in torus. I cannot draw the figure, so it's written in my lecture note. So as I mentioned, string coupling constant GS is proportional to 2G minus 2, right? So that's for genus 0, it's minus 2. So if you go to weaker coupling limit, this term genus 0 is dominant. Whereas if you include genus 1, it becomes the proportional 1. And if you include genus G, it becomes negligible. increase. So that the for weak coupling limit, lambda is fixed, and then take large n limit is weak coupling string theory, or like string perturbation theory is valid. But you can only consider the planar diagram in the type 2b string theory, and compare with the large n limit of the for the n equal to 4 super m melts. So this, in fact, the Marcina actually conjectured in this one first in 97, the late in 97, and a few months later, more concrete proposal has been put forth by two people, two groups at Princeton. I think they already noticed even before the paper of the Marcina's paper appeared on arXiv. So that's why they can be quick, indeed. Of course, one is genius enough to write a paper within a few months. So one group is the Gupta. Sorry, is it G? It's Gupta, right? Okay, can you check? Labanov and the Poincare. And then another is Witten. Another paper coming from Witten. Okay. So they put this proposal more concrete form in string theory. So it's called GKBW is a relation. And I highly recommend you to read this paper. It's a wonderful paper in 98. What was the title? Untitled Chapter and holography or something? I forgot. Let me check now. I should have known. Yeah, Untitled Chapter space and holography. I think, yeah. Even among his paper, it's a top-sided paper. So it's a wonderful paper. Highly recommend you to read. I mean, anyway, so Witten's paper never disappoints you. So anyway, so you should pick one of the paper. So more precise relation is as follows. As I mentioned, so you can just take the Poincare coordinate and the gravitational path integral partition function, where the field at the boundary, you have to impose appropriate boundary condition here. So this means appropriate boundary schematic, but appropriate boundary condition on each field. Phi is equal to some correlation function in CFT. Boundary ADSS and phi 0. Sorry. And the operator. In correlation function. So that's the proposal. So this can be understood as some path integral all the field d phi. Phi can be included metric, gauge field, scalar field, and so on. Everything in string theory, all the field, even all the higher excited mode. Phi and the e to the minus s all the gravitation and string action with phi, where the upper boundary condition is imposed at the boundary. So what are the given the field phi? Is then you how to find dual operator? Oh, the question. Since um, the most so left-hand side is the gravitational theory. Okay, so left-hand side is gravitational theory. So the phi can be gravitational field. So if phi is a metric, is g mu nu, the operator in gravity. So this is gravity side, and this is CFT side. So the operator that coupled to gravity is the most ubiquitous thing. So g mu nu is the everywhere in gravity theory. So given that if you try to consider gravity theory, so you have to consider metric. But CFT, the corresponding ubiquitous operator, and this is second symmetric, is indeed stress energy tensor, energy momentum tensor. So any CFT has the stress energy momentum tensor. Okay, so therefore, any gravitational theory has a metric. So likewise, the dual theory should have the corresponding operator, which is the energy momentum tensor, which is the spin 2. And so how about the phi is mu? So then the operator should be spin 1 is some g mu is the is conserved current conserved current, so that the gauge field in the bulk. So we are considering the following situation. Maybe I should write it like this way. I mean, there is a boundary of it is space. It is 5. And you have a bulk field. Okay. I mean, it's just being schematic. This is you just consider this one is the z direction. At the z equals 0, you have a boundary. And if you have a gauge field in the bulk, so this is bulk, it's called bulk and boundary. So if you have a gauge field, it's a local symmetry. It's a gauge field in the bulk at the boundary. It has to be gauge field is mu. Becomes global the current. So gauge symmetry in bulk becomes a global symmetry in boundary at boundary. So that Nessa current will tell us that if there is a global symmetry, there is a corresponding Nessa current. Okay, that should couple to gauge field in the bulk. So that's what it tells us, and then so and then if you have this scalar field, you have corresponding scalar operator in the CFT. O is scalar operator in CFT. So when you couple them together, the spin has to be. I mean, you have to be contracted Lorentz by Lorentz construction. So it has to be has the same spin. Should have the same spin. And moreover, so in component field theory, if you have an operator, you have a corresponding state, and also you can just have a corresponding the component dimension. So what is the relation between conformal dimension and also interpretation in terms of bulk? Okay. So that's the proposal of this. Sorry, this is I didn't write it down. So this is called GKPW relation. And the proposal is as follows. So if you solve the harmonic wave, I mean, it's given us, sorry. So it is 5, and then so at the z equals to 0, at z equals 0, it phi takes the following form. Either z is d minus, sorry, it is d dimension. Delta or z to the delta. So this is called normalizable mode. Mode, and this is normalizable. There is two solutions. Because it's the second order differential equation. Where delta asymptotic behavior. This is asymptotic at the boundary. But delta is indeed d over 2 plus square root 2 squared d squared over 4 plus r squared m squared. And of course, d is the dimension of the Edis space, and r is the radius of Edis, and m is the mass of scalar particle in the bulk. So this is the Edis. It's a Klein-Gordon equation in the Edis space, okay, which can be easily analyzed. Okay. So to get the consistent behavior at the boundary, so this means that this guy will behave as follows. So if you consider, so this guy will behave phi x and then epsilon, where epsilon is very small, z is equal to epsilon, is indeed epsilon d minus delta phi of. If you impose the boundary condition at the phi 0 at the boundary, but if you push a little bit in epsilon direction on the phi field, then so the Klein-Gordon equation, the equation motion solution will tell us that it behaves e to the d minus delta. So therefore, this strongly suggests that at the boundary, the corresponding coupling operator, so the dual operator at the CFT O should be primary, scalar primary of conformal dimension delta. Okay, so the cancel with minus delta and delta. Okay. So this dimension d indeed cancel with the, of course, I just did schematic. So there is x to the dx is hidden here. So this d dimension cancel with this d dimension. So this is a behavior we expect at the boundary. So the dual operator that coupled the scalar field with mass m should be primary field that has a conformal dimension of this guy. Okay? Conformal dimension of this guy. And I will show you one example in which this proposal is has some concrete proposal. Of course, the example should be it is 5 CFT2 CFT4 correspondence. Okay. So if you solve the Klein-Gordon equation on NS5 plus S5, so this will be phi is equal to 0. So of course this will decompose NS5 plus phi, box S5 acts on phi equal to 0. So this is the massless Klein-Gordon. So simplest case, massless Klein-Gordon equation on the LS5 background. And here, so it is 5 times S5. And here, it just so here you can do the explicit calculations. Sphere, the Laplacian of the sphere is very well known. So the Laplacian of S5 acts on spherical harmonics on such that it has something like the following the condition L plus 4. So which is the eigenvalue of this Laplacian by L. This is the eigenvalue of the Laplacian of 4. So this is called spherical harmonics. Which is the eigenvalue of Klein-Gordon operator or Laplacian on this 5. And this is the eigenvalue. So L it can be understood as an angular momentum of S5. So if you take the S5 as a spherical harmonic and plug that into here, indeed you can forget about the S5 part, and the equation becomes really box S5 plus the of phi L is indeed L plus 4 divided by R squared by L. So this becomes now the mass term. This eigenvalue becomes mass term of the in the LS5 background. Okay. Okay. So now, so the proposal of this GKPW, so this guy. So let's use this guy when d equal to 4. So now we just want to. So let me erase this one. So now d equal to 4, and you just plug this. So now we have d equal to 4, and mass is equal to mass square is equal to L plus 4 divided by R square. Okay, just plug that one into here. Then delta L is indeed equal to 2 plus 4 plus L plus 4 square root. Okay, and then you can solve this equation. You can L square, so L plus 2 L plus 4. Okay, it's very simple. Okay, so let's analyze. So we are now looking at the ADS5 cross S5, whose DL is 40, n equal to 4 super mLs at large N. Okay, large N. And now, so if you look at the L equals 0, L equals 0 is S wave in S5. So L0 is the S wave in at S5. L0 is the S wave in spherical harmonics. So that's what you learn in the quantum mechanics. And so then this becomes massless even in ADS5 viewpoint. Okay? In massless field, then the corresponding operator should have a conformal dimension 4. Okay? So it has to be scalar. Okay, so we consider scalar field in ADS5, and which is massless. So and the corresponding operator indeed can be understood as FE nu. It's the corresponding operator. So remember that this S wave preserves the symmetry. So it rotates. So it's a spherical harmonics, and the S wave always preserves the spherical symmetry of S5. Okay. So therefore this L equals 0 states should preserve SO6 symmetry. So you shouldn't. So the SO6, as I mentioned, it's dimensional reduction. This SO6 acts on X in n equal to super mLs as an M, where M is equal to 1 to 6. Okay, 1 to 6. So this is R symmetry. So as I mentioned, so the 10D super mLs reduces to 40 super mLs by taking decomposition between R 1,3 times T4, T6. This T6 direction rotates SO6 rotated T6 direction. Okay? So therefore, the scalar field is rotated by SO6. Okay? Therefore, the operator shouldn't include the scalar operator. Otherwise, it breaks the SO6. Okay? So therefore, this is a natural candidate, dimension 4 and scalar, and then chargeless. So chargeless. Okay. So this is called Grubel operator in quantum state theory. Okay. The next thing what we can do is, of course, higher state. So now L is non-zero. L is non-zero. In that case, this spherical harmonics is a representation of SO6. Okay. Now it becomes a representation of SO6. Then the corresponding operator should be, as you can easily imagine, as I mentioned, this XM is a representation of SO6. So therefore, you just insert the XI1 IL, and this is symmetrized indices, and the F mu and F mu. And of course, dimension, mass dimension of X is equal to 1. Okay? Therefore, it should have, this dimension should have, so you have an L copy of scale operator plus F mu, which is 4. Okay. So the scaling dimension has to be L plus 4 operator. And if you compare with the calculation by using spherical harmonics, it should be L plus 4. Okay. So therefore, there is a one-to-one correspondence coming from the bulk calculation by using Gleick-Onda equation. And then you have the guessed form from CFD super YAMLs or super conformal field theory at the boundary. Sorry, for the n equal to 4. Okay, so this you can see the relation between operator and then bulk scalar field. So this is one instance, one evidence that support this ADS5 cross S5 gravity theory, and then boundary for the n equal to 4 super YAMLs. Okay, so it's good time to stop. Thanks for taking my course, even though the especially students who did lots of homework. Yeah, but the homework is meant to be created in such a way that you can understand the subject. So once you have found a typo or comments and so on in the lecture note, just let me know. I may put this one in the archive in future. Okay, so let's stop here.